In this video, we'll compute the volume of a region in cylindrical coordinates. So the region we're given is inside a sphere of radius 2, and also inside a cone with the given equation. So the region looks something like this shaded part right here. So to compute volume, we just integrate the function 1 over the region, and we have to convert this into cylindrical coordinates now. And remember, dv in cylindrical coordinates becomes r dz dr d theta. And let's see. The first integral is z, so these bounds should be the top and bottom. The bottom will be the cone. And this equation, if we rewrite it in cylindrical coordinates, is the same as z equals square root of 3 times r. And the top will be the equation for the sphere, which, if we write in cylindrical coordinates, will be z equals square root 1 minus r squared. Or sorry, not 1, square root of 4 minus r squared, since the sphere's radius 2. Now the outer two integrals should describe the shadow of the region in the xy plane, or its projection if we look at it from above. So if we project this region straight down onto the xy plane, you can imagine we'll just see a circle. Now we have to figure out what that circle is. We can do so by setting the two equations equal to each other to see what the intersection is. So the equation for the cone is z equals square root of 3r. The equation for the sphere is z equals square root 4 minus r squared. Now if we square both sides and move things around, we'll see that r is equal to 1. And so this shadow in the xy plane here is the filled in disk of radius 1. And let's actually do it in the other order. Let's do theta first and then r. Doesn't really matter, but let's do it that way. So r goes from 0 to 1, theta from 0 to 2 pi. Okay. So there's no z in the integrand function. So for the first integral, we simply get the top minus the bottom. So we get r times the top minus the bottom. Okay, and the only reason I switched the order of d theta and dr here is because there's no theta anywhere in this function. So we can just get the theta integral out of the way right now. It's very easy. We'll just multiply by 2 pi. And now we don't have the theta integral. Now let's distribute the r here. And actually, let's break the integral into 2 while we're at it. Minus the square root of 3 integral of r squared. The reason I break it into 2 is because the second integral is very easy, we can do it right away. But the first integral, we'll want to do a substitution. So for the first integral, let's do the substitution. U equals 4 minus r squared. So du is minus 2r dr. So this will just be square root of u, and we don't have the factor of minus 2, so we'll make up for that by multiplying by minus 1/2. And let's see, what are the new bounds? When r is 0, u is 4. And when r is 1, u is 3. For the second integral, it's pretty easy. The integral of r squared is 1/3 r cubed, and from 0 to 1. So let's do some simplification before moving on. The bounds here, the 3 and the 4, are sort of in a weird order. Right, the smaller one is on top and the bigger one's on bottom. Let's flip them around and cancel out this minus sign out here. So now it'll be positive 1/2, and the bounds will go in the order we like. And here, r cubed from 0 to 1 is just 1. 1 cubed minus 0 cubed. And square root of 3 over 3 is the same thing as 1 over the square root of 3. Okay. Now, the antiderivative of square root of u is 2/3. So 1/2 times 2/3 is 1/3, times u to the 3/2. And we need to evaluate this from 3 to 4. So 4 to the 3/2. First we take the square root, that's 2. Then we cube it, that's 8. Minus 3 to the 3/2. Take the square root, that's square root of 3. And then cube it. And we're done. We finally have an answer that's just a number. We've done all the integrals. We could simplify it a little more, but we could also just leave it like this, I suppose.